Newton's laws of motion. By the end of this section, you should be able to recall Newton's laws of motion and use them to explain the acceleration of objects. These are the objectives of this chapter. Make calculations using Newton's second law of motion. Identify pairs of forces involved in Newton's third law of motion.
Okay.
And you can see a picture of him, Isaac Newton. Okay, Newton's first law. Now you have to memorize these three laws: Newton's first law, Newton's second law, and Newton's third law. Memorize it with understanding, because they can ask you to write them down in the exam paper. They can ask you to define Newton's first law, define Newton's second law, define Newton's third law. So that's why you have to memorize the definition with understanding, because you can write it in your own words, but there are some keywords that they look for. For example, if you don't mention, say, the certain keywords, you will not get the mark for the definition you write. So the definition should have certain words like resultant force. You know, the word resultant has to be there. So if you say the force is 0, that is not sufficient, because it is the resultant force that is 0 if an object is in equilibrium. So let's see the first law. If an object is stationary, there needs to be a resultant force on it to make it move. We saw how to calculate the resultant force in section 2.1.3. If the object is already moving, then it will continue at the same speed in the same direction unless a resultant force acts on it. If there is no resultant force on an object, either because there is 0 force acting or all the forces balance out, then the object's motion is unaffected. This is Newton's first law. But I think there is a better definition in this book. I can give you that one. Some of the pages here are not there, but we'll see. Actually, I think there was one under momentum. All three laws were given here in this momentum chapter. Last page. Let's hope it is there. Yeah, it's here. See, so this has all the laws. Newton's first law, highlighted in green here, in the green box. You see, Newton's first law of motion: an object will remain at rest or keep traveling at constant velocity unless it is acted on by a resultant force. Very simple. Okay, so an object will remain at rest. That means an object will remain stationary, will remain as it is, stationary. Or if it is traveling at a constant velocity, it will just continue to do that. So if an object is stationary, it will remain stationary. Or if an object is moving at constant velocity, it will continue to move at constant velocity unless an external resultant force acts upon it. So let's say if the object is stationary, it will remain like that forever unless there is a resultant force or external force that acts on it, which causes it to move or change its position. Okay, so same thing applies for the object that is moving at constant velocity. If an object is moving at constant velocity, it will continue to do that forever unless acted on by a resultant force. So this is what you need to remember. An object will remain at rest or keep traveling at constant velocity unless it is acted on by a resultant force. Newton's first law. And that is also given here in a little bit different way. But I think it's easier if you write this definition, because it again explains everything. Yes, any question?
So that means, like, in space, according to Newton's law, like a spaceship or something will keep moving forever or something.
Yes, yes. So if it is moving like that, it will continue forever. But you know, there are other bodies like other planets, asteroids, meteors, you know, comets. They might attract it towards them. But if there was no gravitational field which could produce an external force, then the object will continue like that forever. Yes. Then we have Newton's second law. Again, this is the equation, very important. And you can see this letter here, sigma. sigma is used to indicate the sum of all the forces or the resultant force. Can you see here? Common mistake students make is they write Newton's second law, this equation without the word resultant. If you write it without the word resultant, it is wrong. Okay, so Newton's second law states that the resultant force is equal to the mass of the body times its acceleration, or we can say this is not the most correct way to say it. The correct way to say it is like this. Okay, so there is more than one way of saying it. One is we can say that okay, so here we see Newton's second law. We can say the resultant force is proportional to the rate of change of momentum. Okay, so that is this one. Now you get this from F equals ma, and it is very important that you understand each step here in getting these equations. Okay, so I'll show it to you. Okay, so we have Newton's second law equation, which is F equals ma, and remember this F you must write that it is a resultant force. Okay, so we have F equals ma, and I will use the sigma to indicate that it is a resultant force. Some textbooks don't use the sigma, but it's best to understand, I mean, or even write it to show that this is not just a force, it is the net force, the unbalanced force, the resultant or the net force acting on the object. Okay, now we know the equation for acceleration. Acceleration is equal to v minus u over t. In this, what I'm doing here, each step is extremely important because you will have to use the equation in different forms. Okay, this Newton's second law of motion equation is appearing in different ways. So you have to know each step that I'm going to write here. Then mass acceleration, we can write v minus u over t. Okay, so we get mv minus mu over t. Okay, so you also would have learned about momentum in the O-level class. Also you have learned momentum is mass times velocity. So this is the mass times the final velocity. Therefore this will be the final momentum. So I can use the word F for final and write PF. Okay, so this is the final momentum, and mu, that is the initial momentum, mass times the initial velocity. So this will be the initial momentum. Okay, so final momentum minus initial momentum divided by the time taken for that change in momentum. Okay, so final momentum minus initial momentum is change in momentum. So I can use delta P over T. Okay, so we can say the resultant force is equal to change in momentum over time. Okay. Resultant force, you know, we use this Greek letter delta to indicate change. So final minus initial is change. So that's why this is final momentum minus initial momentum. So it will be change in momentum. So change in momentum over time is equal to the resultant force, sigma F. Okay, I will write the same thing here down. Okay, so what you can see here is that this is the resultant force, and this over here, this is the change in momentum. So what we have here is the change in momentum, change in momentum, okay, then here we have what? The resultant force. This word resultant is very important, okay, because this is not just a force, it's the net force. So resultant force. Okay, then this whole thing here is again the resultant force, right? Because this whole thing is equal to the resultant force. But this you see here, this is what? Change in momentum over time. So what that is the rate of change of momentum. The change in momentum over time is rate of change of momentum. So this is rate of change of Rate of change of momentum.
So momentum is Newton's, right?
No, momentum is Newton divided by momentum is Newton divided by, wait, sorry, you asked about momentum, right?
Yeah,
Momentum, yeah, it has this unit, the mass of unit of mass. Very simple. Here, unit, you can see unit of momentum, unit of P or unit of momentum is what? Unit of mass, that is kilogram, times unit of speed or velocity, which is meters per second. So this is the unit. Okay, well, let me complete this first. Okay, then your questions can get answered. All right, so we have here change in momentum over time, which is the rate of change of momentum. Now if I rearrange this equation, okay, so since I don't have space at the bottom, I will write this at the top here. So we have sigma f is equal to delta p over t, but what I can do is I can move the t to this side. So I get sigma f times t, the resultant force times the time, is equal to the change in momentum. Okay, so we have the change in momentum is equal to ft, and you would have learned that ft is the impulse. Okay, so impulse is equal to the resultant force times the time. Also we can say that is impulse is equal to the change in momentum. Now first I will label what these are. This is the impulse. All these steps are extremely important. Make sure you thoroughly study them, because they can test you on any of these parts here, not only in this chapter but also in other chapters. So that's why I'm teaching you everything here. Okay, so impulse, impulse is what? Force times time, and here we have change in momentum. Okay, it's also equal to change in momentum. Now you ask the unit of momentum. So unit of momentum and unit of change in momentum is the same, because it's momentum minus another momentum. So that means when you subtract or add, the units have to be the same. Now you can see over here the change in momentum is equal to resultant force times time. Now this will have the unit, then Newton second, because this is in newtons, this is in seconds. So the unit of moment is also, sorry, momentum, not moment. The unit of momentum is also Newton second, because this is in newtons, this is in seconds. So this is change in momentum. Change in momentum and momentum both have the same unit. So we can also say the unit of momentum is Newton second. Also the unit of impulse is Newton second. Impulse is change in momentum. So therefore impulse and change in momentum have the same unit. But you know, this is a SI unit, this is also an SI unit, but the difference is this is in SI base units. Okay, now if you break this down to base units and simplify, you will get this. In the very first lesson that we did, we learned about base units. Okay, it's in the beginning of the textbook. Kilogram is a base unit, meter is a base unit, second is a base unit. Newton is a SI unit, but it's not a base unit. All the base units are SI units, but not all the SI units are base units. Okay, so every step here is extremely important. Okay, you should know how to get all of this. You should know how to derive this. You should know how to manipulate this. Okay, and by the way, this acceleration is what? This is what? Change in velocity. So also we can write here, acceleration is what? Final velocity minus initial velocity over time, which is change in velocity over time. So change in velocity over time is acceleration. This is called what? Rate of change of velocity. You see that? You can compare this with this. This is rate of change of velocity. This is rate of change of momentum. Change in momentum over time is rate of change of momentum. Change in velocity over time is rate of change of velocity. That is acceleration. So rate of change of velocity is acceleration. Rate of change of momentum is resultant force. Okay, and impulse is the force times the time, which is also equal to change in momentum. So that is the time. This time is the time period during which a force acts. For example, if you consider the game of cricket, let's say a bat hits a ball. So let's say there's a bat, okay, a bat, and let's say we have a ball. What happens is the bat hits the ball. The ball is initially, let's say, coming this way. It hits the bat and then it goes in the other direction, any other direction. Now the force is applied by the bat on the ball during the time the bat is in contact with the ball. So it's a contact force or impact force. It's a contact force that is applied.
Yeah.
Okay, so the force exerted by the bat is, let's say, F. Then the time is the time period during which the ball was in contact with the bat. Okay, so that force exerted by the bat times the time the bat was in contact with the ball will give you the impulse. And what happens is this will cause a change in momentum of the ball. So let's say in the beginning the ball was moving in this direction with a certain velocity, but now what happens? The direction of the ball changed, and maybe also the speed of the ball changed. So again, what do we have? This delta P is initial momentum is the mass of the ball times its velocity here, and the final momentum is the mass of the ball again times its velocity. And momentum is a vector quantity, so you have to consider the direction. Okay, so that final momentum, this one, minus the initial momentum this way, but since you have to consider the direction, it would be an addition because it's going this way, minus this. Okay, so that will be the change in momentum, which is also equal to this, and that is the impulse. Okay, any questions?
So what's the proper definition of momentum?
Momentum is the product of mass of the body times its velocity. See this equation, this is the definition. If you write this in words, you will get the full credit. So momentum is mass times velocity.
It's newtons per second.
What?
SI unit of momentum is Newton.
Either one is okay. This is SI unit, this is also SI unit. Both are SI units. Okay, so this is the definition, but don't write it only in symbols. If you write it only in symbols, you have to say what the quantities are. So if you are writing a definition, make sure you write it in words. Momentum equals mass MASS times velocity. Write it in words. Okay, don't write only in symbols. It's better to write the equation in words straight away. Okay, then going back to that lesson, now this was very important to help you understand Newton's second law. Okay, now you can see this is one of the definitions. The resultant force acting on an object is directly proportional to the rate of change of the linear momentum of the object. Can you see that here?
Yes.
And also if you look at the definition, I mean the derivation that we did, you can see the resultant force is change in momentum over time. Now this is equal. Here we have a proportionality. Okay, so to convert a proportionality into an equation, you have to add a constant. You have to add a constant. But if that constant is 1, the proportionality and the equation are the same thing. Do you get it? So when you convert this to an equation, it should be F equals K times delta P over delta T.
Yes.
But if the constant is 1, then you will get the resultant force is equal to delta P over delta T. So that is what is happening here. Okay, so the constant of proportionality is equal to 1. You can see they have mentioned that here. To make the constant of proportionality equal to 1. So we can write the second law of motion, which is Newton's second law. Instead of writing with the problem, we can write it like this. So again, this should be resultant force. Okay. All right. So the first definition is saying in terms of proportionality, the resultant force acting on an object is directly proportional. You can see resultant force is directly proportional, this thing, the proportional sign, to the rate of change of linear momentum of that object. So rate of change of linear momentum is delta P over delta T. The resultant force and the change in momentum are in the same direction. Okay, so this momentum is a vector quantity, this is a scalar quantity, resultant force is a vector. Momentum and force are vector quantities, time is a scalar quantity. And they say the resultant force and the change in momentum are in the same direction. All right, so the same thing, same Newton's second law stated in another way. You can see now instead of saying here we are saying proportional, here we say equal. The resultant force acting on an object, is equal to the rate of change of its momentum. So rate of equal to the rate. Earlier we said proportional. The resultant force and the change in momentum are in the same direction. Okay, instead of writing all this, you can also write this. But here there is a minor mistake. Here it should not be just force, it should be resultant force. So instead of saying force equals rate of change of momentum, they should say the word, there should be a word in front of this force, which is resultant force. Okay, it should be resultant force. And here you can also write sigma F, like what I've done here. Sigma F is equal to delta P over. Okay, so that is Newton's second law. So I showed you how to get that from this one. So we have F equals m, where we do all this substitution and we get the definition that was given here. Okay. All right. Sorry. Then Newton's second law. This law tells how much an object's motion will be changed by a resultant force. For an object with constant mass, it is usually written mathematically. Now here we can see clearly the word resultant is there. You have to write this word resultant is equal to force is equal to mass times acceleration. Okay, so yeah, this is how you can investigate Newton's second law. But actually what is done here is you have two light gates. So you can now what happens is initially, let's say the trolley was here, so it is released. Okay, so in the beginning the trolley is stationary, and then you release it so that it starts moving. Then when it passes the first light gate, using the analog and the laptop, we can get the initial velocity here, because this light, when the card passes through the light gate, it initially blocks the light and then it unblocks the light. So using the length of the card and the time taken for the card to pass through the light gate, that length divided by time will give you the initial velocity, because speed or velocity is the distance over time, so displacement over time. So we can say speed is distance over time. So the speed here will be the length of the card divided by the time for the card to pass through the light gate. So initially it blocks, that can maybe start a timer, and then it unblocks the card. When the card initially passes through the light gate, it blocks the light, then blocks and unblocks. So the time taken for the light to be blocked is the time they use, and the length of the card divided by that time will give you the initial velocity. Similarly, same way we can get the velocity here. Okay, so here you get the initial velocity, here you get the final velocity, then final velocity minus initial velocity divided by the time to go from here to here will give you the acceleration. Okay, acceleration is change in velocity over time. So if you get the initial velocity, okay, and if you get the final velocity, and if you know the time it takes to go from the car to the trolley to go from here to here, that is this time here. Okay, so first you have to calculate this, and then you have to get the time between the two light gates. That can be used to find the acceleration. Okay, so here you can see the resultant force is constant. The resultant force doesn't change, because you have some masses here, you have some masses here. So the difference in between the two weights will give you the resultant, because the tension, there is some tension here, there is another tension here. Okay, so this tension minus the tension this way will give you the resultant force. So we are not changing the slotted masses when this is moving, which means the resultant force is constant for each time. So we do it once, we get the acceleration, we change the mass of this, so that way we change the resultant force, and we do it a second time, and then we get another value. So do you see that how they are changing the resultant force? Do you understand this table? So they add some masses here, or they may remove some masses. So in the beginning, let's say they have some weights here, some weights here, then they give the difference that will give the resultant force. And then we can also get the acceleration by using F equals ma. Now I told you how to get A, so we know what F is. F is the difference between the weight of this and the weight of this, that is F. And mass of the trolley, we can get it, and acceleration also we can find. Okay, so acceleration we can find using this equation. Then using those we can calculate the values for different forces or different weights that are hung. You have the resultant force, different resultant forces, and you can get the accelerations for those resultant forces. This way you can plot a graph of maybe like this here, force versus acceleration, or acceleration versus force, and then you get the gradient. From the gradient you can calculate the mass, because F equals ma. So in this example, because acceleration is on the y-axis, this will give the reciprocal of the mass of the trolley, because F equals ma. Okay, so over here what they have is this is on the y-axis, so it's A equals F divided by m, or 1 over m times F. So that's why the gradient here is 1 over the mass. Or if instead, if they had force here and acceleration here, then you know this is your y, this is your x, so the gradient will be the mass. If this was force here and this was acceleration here, but they have plotted it this way because we plot the independent variable on the x-axis and the dependent variable on the y-axis. Okay, the acceleration of this trolley depends on the force. So the more force you have on one side compared to the other, the greater the resultant force and greater the acceleration. So you see that the independent variable is the force. The dependent variable depends on the independent variable. Okay, so the greater the force, resultant force, greater the acceleration. And I told you always the independent variable is plotted on the x-axis, the dependent variable is plotted on the y-axis. Okay, so that's why they do it like this. Now that is one way of doing this and getting the relationship. So it will be a straight line, which is proving Newton's second law. Okay, if it's a straight line passing through the origin, the resultant force is proportional to the acceleration. So you can see here, resultant force proportional to the acceleration, and the constant we get when we make it an equation is the mass. Okay, so this proves that, because you get a straight line passing through the origin, so it proves that the resultant force is proportional to the acceleration, which is what they have stated here. Okay, resultant force is mass times acceleration. Okay, so one way of doing it is by checking how the acceleration depends on the force. Another way of doing it is we can check how the acceleration depends on the mass. So the force is constant. We don't change the masses here or here. Okay, so we keep the masses here and here constant. So the force on the trolley is constant. But we can add masses to the trolley to change the mass of the trolley. So we leave these two as it is. Okay, so that the force on the trolley is the same throughout the experiment, entire experiment. And then we can take separate slotted masses and put them on the trolley here to change the mass of the trolley. Okay, so we change the mass of the trolley, and then same way that we found acceleration before, we find the acceleration. So for different masses of the trolley, we don't need to change the trolley. We can simply put slotted masses on top of the trolley. That will change the total mass of the trolley, and then we get the accelerations. Okay, then we can plot a graph of acceleration versus mass. Now, if you plot a graph of acceleration versus mass, then again we can rearrange this equation and get the resultant force. So acceleration on the y-axis, mass on the x-axis. Okay, so the using the gradient we can find the sorry, it's 1 over mass, because if you plot okay, I'll show you this one also. Okay, so here what they are doing is they are plotting a graph of acceleration versus 1 over mass, because if you plot a graph of acceleration versus mass, it will be a curve. You remember learning Boyle's law?
Yes, yes.
In Boyle's law, you learn that the pressure is inversely proportional to the volume. So we had the equation pressure is equal to a constant times the volume, 1 over the volume. Sorry, 1 over volume. Okay, because PV equals K. If you remember, PV equals K. That is Boyle's law. Okay, so if you plot this graph, what you will get is a curve. You will get a curve like that. Okay, these are asymptotes. The axes are the asymptotes, meaning they don't meet the axis, or we can also say they meet it at infinity. So this goes on forever like that. All right. So, but if you plot a graph of pressure versus 1 over V, you get a straight line passing through the origin, because the pressure is directly proportional to 1 over volume. So here, if you okay, so we get the straight line when we plot pressure versus 1 over volume. Okay. Now we will see this. Okay. So here this graph is what we plotted was here on the y-axis. Here is pressure. On the x-axis we have V. So it is kind of like the relationship y equals K over X. If you are learning mathematics, you would have come across this graph. Y equals 1 over X, or y equals a constant over X. It will be this one, and it is on this side also. Okay, so y equals 1 over X graph. You will have something like this. But if you plot this one, now again I will rewrite this equation. So same thing here. We can, okay, what we have here is this one, P equals K times 1 over V. Now over here what we have is, this is in the form y equals mx. So this is on the y-axis, this is the gradient, and this whole thing is on the x-axis. So can you see it's in the form y equals mx. The y equals mx graph is a straight line passing through the origin. Okay, so that's why you get this. So we are not plotting 1 over V, because if you plot that it will be a curve. So we plot y equals mx, which is P on the x-axis and 1 over V. So P on the y-axis and 1 over V on the x-axis. So that will be a straight line. So similarly, now we have this equation F equals ma. If you apply the same method for this F equals ma equation, Newton's second law equation, F, sorry, it should be capital F, also resultant. Okay, so F equals ma, and if you now the graph is acceleration versus, now acceleration on the y-axis. So I will rearrange this. So acceleration is equal to F times 1 over m. Okay, so this is what they are plotting. So y equals mx. Okay, so here this is on the y-axis, which is the acceleration. The gradient of that graph will be the resultant force, and what is on the x-axis is not m, it's 1 over m. Okay, so I'll circle it to show this whole thing is on the y-axis. Now we can have a look at that. Okay, so we'll have a look at that, compare it side by side. Now can you see that here? So acceleration on the y-axis, on the x-axis we have 1 over the mass. Do you see that? So this is in the form y equals mx. So the gradient of this graph will be the force. Any questions?
So if it is a curve, what will be the gradient?
No, if it's a curve, the gradient is changing all the time. You remember when you learned differentiation mathematics? If it's a straight line, it has a constant gradient, but when it's a curve, the gradient is different for different points. we to find the gradient at any point, we take the derivative of a curve. So this is that is mathematics. Okay. And then if you want to find the gradient of the curve at a particular point, you substitute the x coordinate into the derivative, and then you will get the derivative in dy over dx. That is something else.
The force is constant in here.
Yes, I told you before, we keep the masses here constant. So the force is the difference in the two tensions of the ropes. So the force is applied horizontally. Do you get it? There is a tension force this way, and then there is another tension force this way. Now, instead of having just one, we have two, so that the force is not too high. So we know we can adjust it easily. So the net force is, let's say, this way. So we don't change this. Okay, so we keep the force constant here, but we add things to the top of the trolley to change its mass. We are comparing how the mass changes with how the acceleration changes with mass. Is that clear? Okay, so if you draw this graph, I'll quickly sketch it. Okay, if you draw this, so on the y-axis we have to have acceleration. On the x-axis we have 1 over m, not m, 1 over m. So it is like this, you can see here. So that will be a straight line through the origin. It should be a straight line. Okay, so it's like this. See the Boyle's law, you can compare it with that. And the gradient of this is, gradient is the resultant force. Any questions?
No, sir.
Okay. Then okay, so that is about Newton's second law and how they find it. Can you see this? They are showing now. This is what I already explained to you. Acceleration is f over m, and your this is y equals mx form, but here x is 1 over the mass. Okay, again the same thing. Okay, in this book also they have the same experiment. If you want, you can refer it. The same way, by changing the mass, by changing the force, they're showing you how to do it. Okay, then the last of the Newton's third law is the Newton's third law. Okay, again I will use this one. There is a very nice definition. Okay, that page is missing. Okay, so I'll tell you what the definition is. Okay, here it is. Yeah, Newton's third law, it's here. Okay, Newton's third law of motion. When two bodies interact, the forces they exert on each other are equal and opposite. That is Newton's third law. Okay, so what we can say is, if body A exerts a force on body B exerts an equal and oppositely directed force on body A. So let's say we have two bodies. Okay, let's say we have two bodies. Let's say we have to consider some two marbles or something like that, or two balls. Let's say, so we have one ball here and we have another ball there. It doesn't need to be identical. They can be different shapes, different sizes, or maybe two different objects. It doesn't matter. Okay, so okay, so what we have to do is, now you can see between any two bodies there is a gravitational force of attraction. Okay, so there will be a gravitational force of attraction on this body this way, exerted by this body. Okay, so if you take this body, the arrow I am drawing here is the gravitational force exerted by this body, exerted on this body by this body. Okay, so I will write. Okay, so let's call this A, and maybe we can call this other one B. Okay, so this is the force exerted by B on A. Sorry, exerted by A on B. I'll use this color. So force exerted by A on B. And here we have the force exerted by B on A. Okay, force exerted by B on A. All right, so here we have this. So this is the force. This is the force exerted by B, A on B. This is the force exerted by B on A. So this is object A, this is object B. Now these are both gravitational forces. Now if you take the gravitational force exerted on the earth by the sun, okay, so if you consider this to be the earth, this to be the sun, the gravitational force exerted by the sun on the earth is this one. The gravitational force exerted by the earth on the sun is this one. So this is a Newton's third law pair. Okay, so what Newton's third law states is that if body A exerts a force on body B exerts an equal and oppositely directed force on body A. And there are about 6 criteria for a pair of forces to be Newton's third law pairs. I think that is here in this book. Let's see, look and hope the page is there. Okay, for a pair of forces to be Newton's third law pairs, there are 6 criteria. And not all criteria are given in any book. I'll tell you what those criteria are, but actually this one may give you about maybe three criteria. Okay, but I think it was in this page, so that page is missing. Okay, anyway, I will tell you what the criteria are. Okay, so the two forces have to be the same type. The two forces have to be the same type. They have to act on different objects, and they should be the same size. Okay, I'll actually write it here. Okay, so we'll write it here. So for a pair of forces to be Newton's third law pairs, there are about 6 criteria. A pair of forces to be Newton's third law pairs. There are some criteria. Okay, so about 6 are there, but even with 4 or 5 you can figure it out. Okay, the first one is they should act on the same different bodies. Act on different bodies. Okay, act on different bodies. Okay, then also they should be the same type. Size, same line of action, direction. Okay, so the two forces should act in opposite directions. And the last one is act for the same time. So they should be same time. So you can see here, you look at the shoe, like that impulse force I gave you. Do you remember that example of the impulse? When the bat hits the ball, the time that the ball is in contact with the bat is the same time that the bat is in contact with the ball. So the bat exerts an impact force on the ball, and the ball exerts an equal and oppositely directed impact force or contact force on the bat. So the forces they exert on each other are the same type. You get it? So they are the same type. Now even here, this is also Newton's third law pair. When the boy kicks the ball, the contact force exerted. Okay, first we'll examine each one of these. Okay, so you can see here, this is a Newton's third law pair. How do we identify whether it's a Newton's third law pair? Is if it meets these 6 criteria. The first thing is the two forces have to act on different bodies. You can see this is the force exerted by the shoe on the ball. So this force is acting on the ball, and this force this way is the force exerted by the ball on the shoe. So they act on different bodies, one acting on the ball, the other acting on the shoe. Then they have to be the same type. Both are normal contact forces. Another name for normal contact force is normal reaction force or contact force. Okay, so both are the same type of forces, and they are the same size. Okay, so they will be the same size. The length of the arrow represents the size of the force.
So can't the forces be different?
No, if it's a Newton's third law pair, they should be the same types of forces. They can't be different types. They have to be the same type.
No,
Okay.
no, size, sir.
Yeah, they have to be the same size. So I told you earlier, all these criteria have to be met for them to be a Newton's third law pair. All 6. Yeah. Okay. So same type, same size, same line of action. Okay. So if you draw a line passing through this arrow, along this arrow, it also passes through this other arrow. So that indicates they have the same line of action and act in opposite directions. One is to the left, the other is to the right. Okay. So this is these are contact forces. So act for the same time. So that is the time in contact with which the ball is with the shoe or shoe is with the ball. Okay. Now the same thing we can apply for this also. Okay. So here you have 2 objects, maybe one may be a pen and the other may be a book. Okay. So I model them as a particle, like using a circle like this. Okay. So if you use this one, then check this criteria. Act on different bodies. One force acts on one body, the other force acts on the other body. Then same time, same type. Both are gravitational forces of attraction. Same size. Both are the same size. Okay. Then so this weight is actually mg. This is the weight force, W equals mg. So each one depends on the gravitational field strength of the other. So if you consider, now it doesn't matter if it's a small object or a large object, both objects exert gravitational forces on each other. But this is prominent when they are massive bodies like the sun and the earth, or the earth and the moon, or earth and an artificial satellite. Okay, so if you take this to be the sun and this to be the earth, then this will be one weight force, this is the other weight force. So both will be the same in size. Okay, the size of the forces are the same line of action. Now if I draw a line passing through this arrow, it will also pass through this other arrow. So both arrows are in the same imaginary line, or we can say the same line of action. Act in opposite directions. One is to the left, other is to the right. Act for the same time. They also act for the same time. Okay, so these are the 6 criteria that you should know in order to identify whether a pair of forces are a Newton's third law pair. Now, there can be other forces very similar to this, which have the same size, same line of action, which act in opposite directions, but they may not act on different bodies. So the reason I wrote, and they may not be the same type. The reason I wrote this first is because of that. Okay, so same different bodies, same type. Okay. So this, you can use this to identify whether it is a Newton's third law pair. I'll give you one example where a lot of students confuse. And there are also past paper questions which are related to what I'm going to show you now. Let's say there is a book on the table. We have a book on a table. Let's say this is the table. And let's say this is the book. Brown. Oh, it's brown. Okay, so let's say this is the book. It's on the table. Okay, it's not floating. Okay, it's try to draw it the best I can. Okay, so the book is on the table. All right, now if you draw a free body force diagram for the book, then you have to draw only the forces acting on the book. Okay, so the forces acting, and I will first draw the free body force diagram for the book. Free body force diagram, FBD or FBFD for the book. There, what are the forces acting on the book? One is the weight.
Yes, sir.
Weight. Okay, this is exerted by the earth on the book. Okay, and the other is the normal reaction force or normal contact force or normal reaction force exerted by the table on the book. So where the table is in contact with the book, there is a contact force or normal reaction force also. So it has different names. Okay, normal contact force, normal reaction force, contact force. all mean the same thing. Reaction force. Okay, so let's call that R. So these are the only two forces acting on the book. Now this force is equal in magnitude to this one. That's why the book is in equilibrium. Okay, now if you draw the free body force diagram for the table, okay, I will draw the table here smaller in size. Okay, just zoom, diminish the size of the table. Okay, so I will draw it small so that it's easy. I can manage it in this space. Okay, now the forces acting on the table are the reaction force exerted by the book on the table. Okay, because the book is in contact with the table. So if in any way, if two objects are in contact, then one exerts a contact force on the other, and the other exerts a contact force on the other one. So both exert contact forces on each other. Then also you have a weight force acting. Weight force is the force due to the gravitational field. If this is on the earth, then that is due to the earth's gravitational field. So there is a weight force exerted on the table by the earth. Now let's check. Okay, first now we will draw this. Now usually the question is like this. In the past papers, they ask you a question like this, where you have a book on a table and they draw this one, which is the weight. I will use the brown color so that it's easier. So what they do is, okay, so this weight force is drawn like that. And they also draw this reaction force. Okay, so the reaction force is like this. Okay, now what they will ask you is state why it is equal, why they are equal, and they have given you some choices. Okay, this was a past paper question, and certain students thought it was because of Newton's third law. Now it is not equal because of Newton's third law, because if it's Newton's third law, then it has to meet this criteria. Okay, like I said, these are the two most important, because the others may be the same in most of the questions, but the first two are the most important. Okay, so let's apply this for this example. Okay, and we'll check whether R is equal to W because of Newton's third law. Now if it's a Newton's third law pair, the first thing is act on different bodies. Now are these two forces acting on different bodies?
No.
No, for the book, if you consider the book, both forces are acting on the book. So clearly it's not a Newton's third law pair. And also, are they the same type? Is R the same as W? R is the normal contact force. W is the weight of the book. So they are different types of forces. Okay. So I'll write same type. Okay, then let's check the other criteria. I think other criteria are okay. All right. So it has to meet all the criteria, not just some. So same size. Yeah, they are the same size. That's why the book is in equilibrium. If they are not the same size, then the book will not be in equilibrium. It will move. So here for the book, the resultant force is 0. Okay. For the table also, the resultant force is something I forgot here. There is also a reaction force over here, exerted by the legs of the table. The flow exerts a reaction force on the table, R1, R2. You forgot that. Okay. So the table is in equilibrium also. The resultant force on the table is 0. Okay. Because the table is also not moving. So that means the resultant force on the table is 0. Okay. But this is not what we need to see. Okay. Anyway, let's look at this one first. Okay. So same size. Both are the same size because that's why it's in equilibrium. Then same line of action. You can see both of them pass through the same line. So same line of action, act in opposite directions. Can you see? But they don't act for the same time. Now, if you remove this from the table, then there will be no more reaction force. But the weight force is still there because it's on the earth. So you see these don't act for the same time. So you can even check this one out. Okay, I will use another color. Okay, so you can see these three criteria are met. But these two and also this sixth criteria is not met. So therefore, it's not a Newton's third law pair. So you can use the first two to identify whether it's a Newton's third law pair right away, because these others can still apply to them. Okay, even when it is not a Newton's third law pair. Any question?
So, but still Newton's third law applies there, right?
What do you mean?
So every action has a equal and opposite reaction.
Yes. Okay, so it's not, yeah, these two are not Newton's third law. Okay, now what you are asking is this. Okay, so where is the now you see every action has an equal and opposite reaction. That's what you are saying. It's correct. That is Newton's third law. So I will write that down. Okay, so Newton's third law states that for every action there is an equal and opposite reaction. For every action there is an equal and opposite reaction. Also, we can say another way of saying this is if body A exerts a force on body B, body B exerts an equal and oppositely directed force on body A. Okay, so another way of stating Newton's third law is if body A exerts a force on body B, body B exerts an equal and oppositely directed force on body A. This is Newton's third law. Now, so what is the equal and opposite force for each of these forces? So what we will do here is, now I will show you what that is. Okay, so now if you consider this this book, there is a reaction force exerted by the table on the book. Okay, yeah. So that means there should be an equal and oppositely directed reaction force exerted by the book on the table. That is this one. Okay, so what we can say is by Newton's third law, so the Newton's third law pair is this one. Okay, so what is, yeah, so we have the red R. I will write that red R. Sorry, the red R. I will use the color so that you can identify. Okay, so this R here, R is equal to this R here. By N3, Newton's third law. Do you get it? So the reaction force exerted by the table on the book is equal to the reaction force exerted by the book on the table by Newton's third law. That is the Newton's third law. Now you may be wondering, what about the weight? Okay, so I will try to draw it here. Okay, so let's say this is the earth. That is the earth, and let's say this book, that is the book. Okay, the book is on the table, that is the book. Now there is a weight force exerted by the earth on the book. We call that W. That is this W. Okay, maybe I can use the same brown color so that it's easy for you to understand. Okay, so we have this W. Okay, that is the weight of the book. So now there should be, Newton's third law says that there should be an equal and opposite force for every action. There is an equal and opposite reaction. So the equal and opposite reaction is the weight force exerted by the book on the earth. So that is that one. Do you get it? Okay, so the book also exerts an equal and oppositely directed weight force on the earth, but the earth doesn't move towards the book. Rather, the book moves towards the earth because the earth is gigantic, massive compared to the book. So the lighter object will move towards the heavier one. Okay. Now same thing here also. Now if you have two objects, any two objects that have mass will exert gravitational forces on each other. Okay, so then we can say W equals W by Newton's third law. The weight force exerted by the earth on the book is equal to the weight force exerted by the book on the earth by Newton's third law. That is the Newton's third law pair. N3, Newton's third law. Okay, but you can't say R is equal to W by Newton's third law. R is equal to W by Newton's first law. Okay, this is R. Okay, so for this one we can write R. I'll write it here. R equals W by Newton's first law. Or also we can say in terms of Newton's second law also. Okay, if you want by N2 also we can explain why it is equal. Okay, so if you say by Newton's first law, you can see it is stationary. It is in equilibrium. It is in equilibrium, the book. Okay, the book is in equilibrium because the resultant force on the book is 0. Okay, so this is for the book. For book. Okay. So by Newton's first law, which states that if the object is stationary, it will continue to be stationary like that unless acted upon by an external force. So no external force here. These forces are balanced, so it's stationary. Also, we can say by Newton's second law, no acceleration, no resultant force, so it has to be stationary. Any questions?
No.
Okay, so these criteria are very important. Okay, you should study them. You should remember them. In the exam, they can ask you a question like what like this example I explained to you. Okay, so right here itself they have it. You see that in terms of Newton's laws, explain why this book will sit stationary on a table. So you have to say here you should not say about Newton's third law. You have to explain in terms of Newton's first law and of second law. Okay, so here are the definitions. In summary, Newton's first law of motion, an object will remain at rest or in a state of uniform motion until acted upon by a resultant force. Newton's second law, if an object's mass is constant, the resultant force needed to cause an acceleration is given by the equation F equals ma. So, there is more than one way to give the definition. Okay, so make sure you write one of them and it has the necessary words or the equation. So if you write this, make sure you write the equation. Then Newton's third law, for every action there is an equal and opposite reaction. That is exactly the same thing I wrote here. For every action there is an equal and opposite reaction. Another way of stating Newton's third law is by this. If body A exerts a force on body B exerts an equal and oppositely directed force on body A. So you see, that's why they have to act on different bodies. Okay, again, if you look at this example, so Earth exerts on the book exerts on the Earth, equal and oppositely directed, same size. Here, the reaction force. Okay, by Newton's third law. So the book exerts a reaction force on the table and the table exerts an equal and oppositely directed reaction force on the book. All right, that's the end of Newton's laws of motion. So we discussed all three laws: Newton's first law, Newton's second law, and Newton's third law. Any questions?
No, sir.